Let's start with a simple problem. We have this body at position 0 at time 0 with a force of order 1 with a magnitude of 2 and a force of order 2 with a magnitude of 2, all in the same direction and a mass of 1. What is the position of the body at time t? In real-life physics, to calculate the acceleration of a body with many forces applied to it, you can just add all of the forces applied to that body to calculate the net force, and then divide by mass to get the acceleration. Then the position of the body is just 1/2 of the acceleration times time squared. But in the problem I presented, we can't do that. The forces have different units, so you can't add them. However, it is possible to calculate the position of the body at time t. I'm using it to make this animation. So how did I do that? Force of order n is mass times motion of order n. So the motion of order n is force of order n divided by mass. Applying this to our problem, we get that the motion of order 1 is 2 and the motion of order 2 is 2. Now what? Well, the motion of order 1 is velocity and the motion of order 2 is acceleration. And I want at school that we can use this formula to compute the position of the point at time t, given its initial position and initial velocity and constant acceleration. By substituting the values for velocity and acceleration, the final position is given by this. We now have the position of the body as a function of time. Now, what if instead of an order 2 motion, we had an order 3 motion? Order 3 motion is jerk, which is not on the formula. To be able to solve this problem, we need to generalize this formula first. Remember that the motion of order n minus 1 is the integral of motion of order n with respect to time. We want a formula for position, which is motion of order 0. So for a motion of order n, we can find the position of the body by integrating the motion of order n times with respect to time, which results in 1 over n factorial times time to the n plus terms involving the integration constants, which corresponds to motions of smaller orders. So to get the position of a body with many different motions at time t, you calculate 1 over the factorial of the order of the motion times time to the n, and add all of the values. So this is a generalized formula for the position of a body with many motions, or using sigma notation, this. If you don't know sigma notation, this is the same thing as what I wrote before. Sum up all of the motions of order n divided by the factorial of n times time to the n. Replacing motion with force divided by mass results in the formula for the final position as a function of the forces that act on a body, the mass of the body, and time. Another way to write this is that if the motions of one object are subscript 1m, subscript 2m, etc., where the left subscript doesn't correspond to the order of the motion, the position is given by this, where the function no outputs the order of the motion or force, and I is the index for the motions or forces. These formulas mean that the final position is a polynomial function whose input is t and there isn't a limit to the degree of the polynomial, as the motion can have any order. I would also like to introduce a convention that allows the sum of motions and forces of different orders. If you have a body with a motion of order 2 with magnitude 4 and a motion of order 4 with magnitude 5, you can say that the body has 4 units of motion of order 2 plus 5 units of motion of order 4, and the same for forces. This makes it easier to talk about bodies that have multiple motions or forces of different orders, even though it is usually not valid to add quantities with different units. In summary, to find the position of a body with many motions or forces at time t, you can use this formula, which results in a polynomial expression in t, and by evaluating the polynomial at time t, you can find the position of the body at that time. This is all I have for this video. Goodbye.